floor is yours.
Yeah, thank you very much for the kind invitation. Can you hear me?
Yes, yes.
Yeah, thank you very much.
Yes, we can hear you very well. We can see
for
your
organizing
presentation.
this seminar. I have the greatest respect for the work you do, for especially here for organizing here seminar conferences and the workshop. Here, this workshop, I have here, so I have to click to OK. So, dedicated to the anniversary here of Julius Wess and Helmut Rauch. Helmut Rauch, I was observing the group for a long time before I went to Vienna from Heidelberg University. Heidelberg University is 1 flight hours away and or 700 kilometers. And the position I had at Heidelberg, and when I looked in the direction of Vienna, my view was blocked by our castle. So I had a very romantic view of Vienna at that time. Here of the Stephansdom and the fairy tale. And there was this amazing group of Stefan Rauch. Here a picture of 2003. And here a picture, a recent picture here with Yuichi Hasegawa, Stefan Sponer, here Hartmut Lemmel, Richard Wagner, yeah, Armin Danner. And yeah, they did these amazing experiments where they took a beam of neutrons, split it in 2 parts, and they recombined it. The experiments there were exciting. The outcome was sometimes not what you expected, because he made these experiments where intuition fails and results are driven by poor chance, but they are astonishingly nice and driven by clear aesthetics. And we were standing in front of nature and just wondering also what can be described in a simple mathematical way that has a certain beauty and is usually right. So his fame here made us awestruck, and we had a lot of respect. Here's another picture of this interferometer with the phase shifter. And when you here move this phase shifter, yeah, the thing is that you split the neutron, and when you change the phase here, the upper neutron has to decide whether his goes to the direction A or direction B. What we learned in the university about the size of a neutron, 10 to minus 15 meters, the experiments of Helmut Rauch has shown that the coherence length of the neutron is much more. It's on this picture, it's about 100 nanometers. And when you put a neutron on a table, the Schrödinger wave size is about 100 microns. That's another nice experiment what Helmut Rauch did with Hartmut Lemmel, some sort of quantum mechanical neutron break. You take a neutron, it's passing through a slit, and now you have the problem what you learn in first classes of quantum mechanics, a particle between walls. When you move the walls together, then the energy goes up. Here, the change is very small because the slit width is 33 micrometers for a de Broglie wavelength of 0.18 nanometers, 18 angstroms. For a neutron with an energy of 25 milli-electron volts, but when it goes through the slit, it has to obey the boundary conditions. And Helmut Rauch and Hartmut and other co-workers were able to observe a change in energy of about 1 pico-electron volts. This is the experiment, how it was performed in the neutron interferometer. I want to mention another very famous experiment, the verification of coherent spinor-rotation of fermions. It's the first demonstration here that you have to rotate a neutron twice before you get it in the same state again. 2 pi and then another 2 pi, 4 pi, what is now used in every quantum computer. One may ask, is a neutron a Schrödinger cat? A Schrödinger cat has 2 states, the state dead and the state of alive. The neutron here is left and right, and my colleague Markus Arndt from Vienna University, in a talk, he defined the Schrödinger cat as being complex, warm, and macroscopic, to be simultaneously in 2 distinct states, and it contains at least 1 biomolecule. So unfortunately, our neutron, it's not a Schrödinger cat. But what we've shown is that the neutron is a quantum Cheshire cat. Alice in Wonderland, she was wondering whether a cat, you see it here, a cat with a grin, that the cat could be without the grin, or the grin could be without the cat. So in our interferometry, the grin is the spin and the cat is the neutron. So it looks like that the spin is moving one part and the cat is another part. This is an example of an entanglement between path and energy, and I am quite happy that Anton Zeilinger in his Nobel Prize lecture, he was mentioning the Greenberger-Horn-Zeilinger states, also what you use in every quantum computer today. It's an entanglement of 3 different particles, and Yuichi Hasegawa and Helmut Rauch and co-workers, they were able to do a Greenberger-Horn-Zeilinger state with just 1 neutron. What you see here is the entanglement between path, energy, and path, energy, and spin state. In the meantime, experiments here driven by Hartmut Lemmel, and especially in a collaboration with Enrico Massa from INRIM here in Italy. INRIM was participating in the redefinition of the kilogram in the Avogadro project. Here, this team managed to increase the sensitivity by an interferometry, which is defined here by the length between these 2 plates, and for some experiments by the area here in between. So when you split an interferometer, it's possible then to increase the sensitivity, and this was quite successful, as you can see in this picture over there. And together with the University of Vienna, they were building diffraction gratings using diamond nanoparticles. here in this picture, a box is shown where you have monomers and you shine light on it. And with these monomers, they polymerize with a spatial light pattern. And it forms now an interferometer, which is very stable for a very long time. So with the new split crystal and this polymer interferometer, together with ultra-cold neutrons, we have now a working group we call Next Pi neutron interferometer experiments on quantum states at the pico scale. These are experiments with thermal neutrons using the setup at the ILL, as is here called S18. Then the very cold neutrons with the polymers and ultra-cold neutrons. The thermal neutrons we do exploring the quantum world with superposition entanglement. With the very cold neutrons and ultra-cold neutrons, we are exploring here possibilities for searching for new physics, where we search for dark matter model, dark energy models, or search for hypothetical forces, or a search for a neutron charge. It's Quantum Austria initiative with the TU Wien, University of Vienna, ILL, and INRIM in Italy. When we put neutrons in 1000 quantum states, that's the experiment I want to show with ultra-cold neutrons. This is the setup. We have to move to Grenoble, to the European neutron source. This is here a picture from my flight to Grenoble last year when the weather was fine. A picture out of the window. Grenoble is located here. They call it the capital of the Alps. The ILL is next to the synchrotron, which you can observe from the airplane when you move closer and closer. This is the synchrotron, European synchrotron, ESRF, and this is the ILL, the Institut Laue-Langevin, the European neutron source. And Helmut, he was in charge of negotiating the membership of Austria at ILL, which made it possible for us to do these experiments. The beam position PF2 with ultra-cold neutrons here with Tobias Jenke and Peter Geltenbord. Here you see a nice picture between Helmut and Peter discussing here the option to, it's a pumping option for ultra-cold neutrons here published by Helmut Rauch, where he had the idea to go the other way around. Usually you start with very hot neutrons, make them cold and then ultra cold. He goes the other way around to use ultra cold neutrons and then to give them a kick and produce cold neutrons. This is shown in this picture, a demonstration experiment at PF2, and it was quite successful. The experiments we do with ultra-cold neutrons, again at the beam position PF2, this is what we cannot do in Vienna. At ILL, you start with fission neutrons with 2 mega electron volts. they thermalize in a heavy water tank and have then the energy of 25 millielectron volts. Next to it is a cold source made out of liquid deuteron at a temperature of 20 Kelvin. The neutrons entering this cold source, they thermalize to that bath with about 4 millielectron volts. And as there's no other cold source, the ultra cold neutrons we use, they are taken out of the lowest part of the cold distribution, which has a maximum of 800 meters per second. The neutrons, which are ultra cold here below, they have about 7 meters per second, and it's a small fraction. It's about a 10 to minus 7 part. Ultra cold neutrons are distributed by the so-called turbine. Neutrons move up, and then there are several exits. So one of those is used by our experiment. Here you see the curved guide, the turbine, and then experimental platforms. For the future, we will do experiments at this platform over there to the right. The experiment has the size of a bath tube. Ultra-cold neutrons are that cold that they reflect on surfaces. So you can take a neutron, let it fall in the gravity potential of the Earth until it's reflected from a mirror. When it comes close to the surface, we need quantum mechanics to describe the results. So here you see the Schrödinger equation for that problem in z direction against gravity, with the gravity potential mass of the neutron, acceleration of the Earth, and distance in direction z and y. There is no force. Now, when you apply a characteristic length scale of about 6 microns and an energy scale of 0.6 pico electron volts, and you apply a change of variables, then you arrive at Airy's differential equation, where the solutions are called Airy AI and Airy BI. Here, Airy AI in red and BI in blue are shown. Airy AI looks like a sine wave with an exponential decay. BI looks like the cosine, which goes then to infinity. For quantum particle, the exponential decay, this is where the particle is classically not allowed. And this mathematical function is now defining the energy states of our neutron on the mirror. To put this mathematical function on that mirror, we have to shift our Airy function and to scale it. To scale it with natural constants, with h bar, with the mass of the neutron and the acceleration of the Earth. and now it's quite straightforward. The solutions are an infinite number of these array functions. Here I have plotted the first 200. We are working with the first 20 states shown to the right, and we can drive transitions between these states. When we oscillate the mirror underneath, we can drive transitions. It's in the acoustic regime. For example, if a neutron is in state 5 and you vibrate with a frequency of 445 Hertz, you drive the transition between 5 and 8. It's like a two-state transition. The other states, they are just observers, shown here on the Bloch sphere for these two states, 5 and 8. It's what we have built is a simple gravitationally interacting quantum system with a neutron with a mass and a spin, which is falling in the Earth's gravity potential, and a neutron reflector made out of glass. This works because this glass has a potential of about 100 nanoelectron volts. Of course, for reactor neutrons, thermal neutrons with 25 millielectron volts, they practically don't see the mirror and they can go through. But our ultra-cold neutrons, here with a velocity distribution of about 7 meters per second in the horizontal direction, they have an energy which is below these 100 nanoelectron volts. Many years ago, we have demonstrated these quantum states with the setup underneath, where we have a bottom mirror and an absorber on top. You can move the height of the absorber, and you can adjust it in such a way that only neutrons in the ground state can go through. In our experiments today, this is our state selector to put neutrons in the ground state, and then we can manipulate them and do spectroscopy. Here is an example when a neutron is here on our mirror, and then here is a step. The ground state at 1.4 picoelectron volts, and if there's another neutron here 30 microns higher, it's here also in the ground state, but shifted by 30 microns. Now, if the neutron is moving and falling down the step, the probability to find the neutron is shown here. It's 0, and then here the wave function squared as a probability to find the neutron. It's 0, and then we have this distribution. Our neutron here is not in an energy eigenstate anymore, and we have to construct it with our array functions. Array functions are a complete set of functions. If above the mirror, if our function is sufficiently brave, differentiable stepwise, And then we can adjust this wave function with an infinite sum of area functions. As you see here, all these states going up to infinity give this wave function over there. It's in a superposition of these states here. And now if our neutron is falling down the steps, it's an interference, what you see of all these infinite area functions. Our neutron is going down, it's going up and going down. It's the interference of an infinite number of area functions. After a certain period of time, you cannot say whether the neutron is going down or going up. You call this a collapse of the wave function. And later on, you see revivals. The revivals start now. It's again going up, going down, going up, and going down. In blue, the center of gravity for our neutron. In white, it's the center of a classical particle, which is also going up and down. And you see the classical particle and the neutron, they are out of phase. At the beginning, they are in phase, and later on, they are out of phase. Of course, this has been known before. It's a quantum phenomena. What we observed when we did the calculations is that neutrons are disappearing here on the top, although the starting wave function has an exponential decay. When you plot now our quantum bouncing ball on a logarithmic scale, you see that our neutron is moving all the way up. The probability is not so high, it's below 1%, but we think it's observable, and we try to observe it in the next experiments next year at ILL. We have already started, and we see and have preliminary results. Here, this is really going far up. In here, a micrometer scale, 150, 200, 250, 300, 350 microns above the mirror. Our observation of the problem in white, a measurement with spatial resolution detectors. In colors, our simulation. The neutron is falling the step of 30 microns. It's going down, it's going up. Then another observation. It's going down. We can clearly observe here this interference pattern with our neutrons. That this is not going to zero is due to the fact that our spatial neutron detectors have a resolution of about 2 microns. Our experiment at the ILL, made out of mirrors and a control system, the mirrors, and then capacitive sensors to make sure that all these mirrors are are in parallel, that there are no steps, and that they are horizontal. We also use a laser interferometer system to control the setup. This is our so-called Rabi setup. It consists of 3 regions. Region 1 is our state selector. Here, when you zoom in, there is a flat bottom mirror. On top is a rough mirror. The slit size is about 30 microns. Neutrons, which are in the ground state, they can easily pass. Neutrons in higher states, they have an overlap with the rough surface, and they are scattered out of the system. This is our state selector, which I have shown at the beginning of this.
Немало по розкладу. Ні, немає. А звідки ж немає? Немало по розкладу. Що це таке?
Ні, це виключилось все.
Це не через обігрівачі, ні?
Ні, світло виключилось повністю.
Then another oscillation mirror, and then the final.
Professor ABELE, I'm sorry, we had a problem with electricity, and last few minutes we couldn't hear you. And
Okay.
can we interrupt just for 1 minute to switch on our projector once again? Just a minute, I will let you know when to start. I'm sorry for this problem. Now we start our beamer. З розкладу. Okay, so we can continue once again. Professor ABELE, sorry for these technical issues. Please share your screen.
Yeah, where should I continue?
We can see your presentation. You do not share. Please share your screen.
Yes. So.
Now it starts. Okay. Yes. We were exactly here, and you described number 1. These 2 mirrors, several microns between these surfaces. I remember. So we stop here in this place.
Yes, I was explaining our Rabi setup.
Yeah.
And now I move on from Rabi to Ramsey, where we replace our 3 regions setup with 5 regions. Here, this is the 5 region setup. First region is the state selector. Then the second region where we use oscillating mirrors. Then we have a time of flight region and another oscillating mirror, and then the final energy state analysis. So this is the 5 region setup. When we prepare the neutron at this position, it's in the ground state. When we oscillate the mirror, we put it in a superposition here for this experiment, in a superposition between state 1 and 6. And in this superposition, yeah, it's moving coherently from region 2 to region 4. Now in region 4, with this second oscillating mirror, we can, for example, vibrate it in phase or out of phase. This is seen in this picture on the left. If you vibrate the mirror in region 4 in phase, you bring the neutron all up into state 6 so that it cannot pass through the state selector, and you have here a decrease in count rate at the neutron counter at the end. If you vibrate out of phase, then you bring it back again to state 1 and it can pass, and it's the count rate is in the upper state when you are on resonance. So this is the 1 to 6 transition we were measuring here. Some information about the experiment. The velocity range is between 4 and 11 meters per second. The potential, as I mentioned, is 100 nanoelectron volts. The length of the setup here is almost 1 meter. The distance between the mirrors is about 30 microns. And the step between the mirrors is less than 0.5 microns. The typical count rate is 20 millicouts per second, and the alignment relative to G is 10 microradians. Here you can show here results of the Ramsey measurements as a function of frequency, count rate in the detector. This is the 1 to 6 transition, and this is 2 to 7 here blown out. And when you change the phase between the two oscillating phases, you can sweep through. So, is this useful? What can be done with such a setup? We can search for hypothetical gravity-like interactions which could couple to our neutron. Again, on this slide, the Schrödinger equation with the gravity potential, but hypothetically, there could be another potential. For example, what is shown here to the right, it could be that the spin of the neutron here in this Feynman diagram couples to the mass of the mirror via axion exchange. This is a pseudo-scalar-scalar interaction, and if it would be there, it would change our energy states we see here. When we don't see it, we can place limits on such axion interaction. And another example is a symmetron field which has been used to explain the expansion of our universe. If it couples to our neutron, it would also change here the potential. Other examples are shown here, how the neutron here could couple to hypothetical models. The first part here about dark energy and dark matter models. A recent paper here with Fischer et al. About for environment-dependent dilatons. This is about chameleons, which is already now ruled out. And this is about symmetrons. Then there was a proposition of Erik Verlinde, whether gravity is an entropic force. And then there's the question about gravity theories based on geometries other than those of Riemann, Cartan, etc. Many effective field theories arising cannot be described in a Riemann background, but you can write down a Hamiltonian and see the effects on our system, also whether Lorentz invariance is violated. Another class of experiments is related to neutron beta decay. These experiments are performed at the University of Munich. We have planned and built a huge instrument. It's about 12 meters long. It's called PERC. It has been delivered in September 2021 to the reactor in Munich. Here the delivery process on the right, how it has been set up at the university reactor. I'm now in Munich right now. It's a user meeting. It's a user meeting without neutrons because the delivery for neutrons stopped 4 years ago, and I am now eager to hear when the neutrons will be back at the reactor in Munich, that we can do the experiments. The idea is here to study the structure and nature of weak interaction and possible extensions of the standard model. This is part of a priority program of the German funding agency and the German and then the Austrian funding agency, FWUF. The advantage of neutron beta decay is that in the standard model, there are just 2 parameters. Here it's the CKA matrix, and it's the ratio of the axial to the vector coupling. But there are many observables, so many tests of the standard model can be done, and the whole system is overdetermined for searches for physics beyond the standard model. So if there are hypothetical particles, SUSY, C, and so on, then it can be observed. Earlier results of our work here, searching and measuring correlation coefficients, electron asymmetry A, neutrino asymmetry B, and proton asymmetry C, can also used to help to solve the neutron lifetime puzzle. when neutrons are stored in a box, and you determine the lifetime when you count the neutrons as a function of time, then you get this lifetime, which is below 880 seconds. When you use a beam experiment, then the lifetime here is much higher, and there is a 6 sigma deviation. It has been suggested that a neutron could decay into dark matter particles, but there are no indications for that. So neutron beta decays are quite important, because here a list of Dirk Dubber's processes with the same Feynman diagram: primordial element formation, solar cycle, neutron star formation, pion decay, neutron detectors, and WNC production. Determining GA over GV is a difficult task. It was 1.19 in the 60s, then it moved up in orange. These are our own experiments where we improved on the error bars here from 300 to 56. So, okay, I would like to come to an end. The experiments I was referring to concerning gravity, here it's a collaboration between TU Wien, Vienna University, ILL, Grenoble, TU Wien, and Tulane University.
Just a moment. We have some problems once again with electricity.
Це зараз знову вимкнуть, і воно ще раз таке саме. Якщо знову вимкнуть, то...
Ваня. Professor ABELE, I'm sorry, we have problems once again with electricity. Just a moment. Just a moment. Can you hear us?
Yes, I can hear you.
Okay. I'm sorry. Once again, we had a switching from electricity system of our city to our local generator, and after that, once again back. So it's happened sometimes. And as I understand, you almost finished, and we were listening the last one slide, probably with acknowledgements, and after that we can go to questions. Am I right?
Yes, I was finished.
Okay. So, dear colleagues, we can hear you, and we can continue in this mode. Just probably a few seconds, and let us thank the speaker.
Yeah, thank you.
Thank you very much, Professor ABELE, for such really interesting lecture. And please, dear colleagues, ask the questions. Professor Lev.
Okay, I am born on Lev. Thank you very much for a very interesting talk. But I have only two questions. First question is, well, do you can experimentally determine difference between different presentation wave function? It is a complex function, spinor, or a Clifford number. It is possible experimentally determine a difference.
I'm not sure whether I understand the question correctly. You're talking about the degrees of freedom in our system. So we have
As I understand, the difference between different wave functions. Yes.
Presentation wave function. Yeah. Okay. In quantum mechanics, I can determine a wave function as a complex function, or a spinor, or a Clifford number. What is difference between this presentation in experimental setup?
When you were talking, you were disrupted. So what I hear is so the difference in our description concerning the degrees of freedom. So we have the degrees of freedom of spin in our neutron. So there is of course spin up and spin down, what you use in the NMR technique, for example. When you apply a magnetic field, this provokes the Zeeman splitting, and you can drive transitions between spin up and spin down. If you put the neutron on the mirror, you have bound states of the neutron, and you also have different states. In contrast to the spin state with spin up and spin down, there is an infinite number of energy states, but they behave in one way or the other like a spin half system, because the resonances are in such a way that you can drive transitions between two of these quantum gravity states in such a way that the other states are practically not involved. So it's a similar system, and one can call this a pseudo spin system in some respect. And now, of course, one can use both. One can use the spin degrees of freedom, and one can use the gravity degrees of freedom.
Thank you.
The second
But I have another question. What's the change in interference picture if you change the size one hole in classical experimental? Okay, you can change the size of one hole in classical interference experiment. What change in interference picture? Do you know or no?
I mean, our slit is related to that problem of a hole. Yeah, you have the interference effect of a hole, and in our case we have these long slits. This is in some sense comparable in that sense that the hole is small and the slit is long.
Thank you.
Okay, thank you very much. Other questions? Okay, Professor Semenov.
Yeah, so thank you very much for your interesting talk. Here. I have just a question about your experiment. Is it really possible to use such kind of experiment with neutrons for the purposes of quantum sensing, for example, gravimetry or accelerometry, like it is used with cold atoms? or they're not really white? So is it not fantasy? It's possible to do or not?
Well, you need a reactor to do the experiments. So it's not like a device you move from one place to another. Our advantage of neutrons is that the magnetic moment is much smaller compared to atoms, and atoms, they stick when they come close to surfaces. So what we are here probing are hypothetical forces which are test of Newton's law at short distances, but what you cannot do with atoms because they stick.
But probably a related question. In these experiments, you can, as I understand, you can use the constant G. This is gravitation constant. Actually, you can measure using these experiments or not.
Yes, and yes.
Or you use
I mean,
this constant as constant in your calculations after yes, when you treat your experimental results. So probably this constant you use as some already known value.
It depends. It's a question of sensitivity.
Yes, and this
The Ramsey spectroscopy, it's some kind of quantum technology which allows experiments with the highest sensitivity. Ramsey spectroscopy has been used to search for the electric dipole moment with an energy resolution of, yes, it's maybe I'm looking whether I can find this.
Unfortunately, we cannot see your presentation. You do not share it. When the electricity switched off, the presentation disappeared. But we can see you. We can see and we can hear. You can share the screen, and we can.
I'm just wondering. It's about the sensitivity of experiment with neutrons. And so I can try to find. So let's see. So 1 second. Sorry. Also have to find this. Yeah. So here it is. So there I have some. Now you should see.
Yes. Now we can see your presentation.
So here is searches for the electric dipole moment. Is it the usual setup what has been invented by Norman Ramsey, where you have a quantum system with a two-level system and then a coupling with the magnetic moment in an outer magnetic field, and now you drive transitions with the radio frequency fields, and it has an amazing sensitivity, so that this is used in atomic clocks with the Semenov technique, or searches for electric dipole moment, and it consists of 5 regions.
Yes.
In the last years, the improvement is enormous, and this is a presentation here adopted from Klaus Jungmann, and this presentation is by Klaus Kirch, where you see a comparison of the electron with the atom, with the neutron. And you see here in blue, it's the neutron, in orange, it's the atom, and then in green, the electron. it looks a bit that the neutron is left behind. Here, the progress by the neutron, but this is the result on the electric dipole moment. When we plot it as a function of energy, the most precise one here is the neutron and the mercury. So the atom is on the energy scale 4 × 10⁻18, but there's a huge amplification factor inside, so that the limit on the electric dipole moment is larger. It's 9 × 10⁻29, whereas it's only 3 × 10⁻6 for the neutron. But what's important when you want to measure, for example, big G, then it's the overall sensitivity in energy. And for that energy resolution you have here, you would improve on big G by a fair amount. Unfortunately, with our experiment, we are not there at the moment. Our spectroscopy is on that level at the moment. Ramsey spectroscopy with gravity resonance spectroscopy, what I have explained in the talk. So the good news is that we are using the same ultra cold neutrons. So from a statistical point of view, we can go there from 10⁻17 to 10⁻21. So that the trick for the electric dipole moment experiment was to store neutrons and to improve the sensitivity by a factor of 1000 or so. And to go in this direction, we have to do the same steps. We have to store our neutron instead of having a time of flight region of several milliseconds. When storing the neutrons for several seconds, it's a gain factor of 1000, and we are working in that respect, and hoping that we are able to go in this direction. Of course, it's a bit difficult to make a prediction for many orders of magnitude, but from the statistical point of view, it should work.
Okay, I see. Thank you very much. Dear colleagues, let's thank our speaker again. Thank you very much, Professor ABELE. And the next lecturer is Professor Andrii Semenov. And the lecture is titled Unveiling Optical Nonclassicality with Realistic Photocounting Measurements. So we are in our program, and we have lecture within 50 minutes. Professor Semenov, please.
Yeah, just a
the floor is yours, but keep some minutes for the questions.
Okay, yeah. Okay, it's just a moment, just presentation should appear and the full screen. Yeah, it works. Yeah. Okay, thank you very much, Sergey, for a nice presentation, me introduction. Yeah, and first of all, I'd like to thank the organizers from both Ukrainian and Austrian side for giving me a possibility to present some results of our group for this talk. Also, thank you very much for people in both countries for being here and for hearing our results. I just remember my visiting together with my PhD student, Mikita Klen, Wien. It was in 2021. We have visited the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences and the whole city in Vienna. So this is really impressive quantum ecosystem. This is really great things. We got some data from the group of Professor Rupert Ursin there. Only now we start to understand how to deal with this data and maybe get some results. Okay, what about today? I will talk today about, so my talk today will be devoted to a traditional quantum optical question. So this is not so fundamental question as it was in previous talk, but what I would like also to say is that this part of my talk, I just want to apologize in advance that people in part of audience were hearing part of my talk, but nevertheless I will also promise you that I will present to you results. Okay, my talk about just a moment, doesn't work. Yeah. So my talk will be devoted to a phenomena which called optical nonclassicality, and actually this is a point which was a subject of Nobel Prize in 2005. That 1/2 of the Nobel Prize of Professor Glauder were awarded for this, and for his contribution to the quantum theory of optical coherence. In particular, this is related to the question which is really interesting and maybe not, people consider it as not really fundamental, but nevertheless useful, which calls optical nonclassicality. Just few slides to remember what is it. So again, does not work, sorry. And now it works. Okay, so as when we read Nobel lectures of Professor Glauber, or when we consider maybe some very basic papers, so the question appears very, very early, so at the beginning of quantum optics, so this is 50th year of the last century, so 1955, so in the very well-known experiment by Hanbury, Brown, and Twiss, they had a problem. They wanted to measure, and this is from astronomy problems, they wanted to measure the angle size of stars. And they were doing it in radio frequency, but also some mock experiment has been done in optical domain. And while people were talking about radio signals, that okay, this is very clear classical signal. In optical domain, it was argued that one should use in this case something like quantum description. In principle, experiment looking like this mock experiment. So you have a source, your light beam is split in two ways, and after that you have here detector. This detector distance can be shifted, and here you consider simply correlation between clicks on these both detectors. And the results were like this. So this is a bit ridiculous that this experiment can be explained totally with classical optics, and even more. We can also consider so-called coherent states, even such things can be considered in quantum optics, so this dependence of correlation coefficients from this distance d. However, there are other very interesting behavior in this case, something like this, which is already unexplainable in classical optics. And this is a very good question to understand which phenomena can we explain. So when we should consider quantization of electromagnetic field for description of optical effects, and when we use simply classical electrodynamics. In principle, no, this is just some units, so don't consider, because this, in order to say meters or centimeters, I should also say about wavelengths, about other things, and I just don't want, it's simply just some funny numbers and nothing more. Yeah, but thank you very much. Yeah, it's so better not to write these numbers. Yeah. And what is from the theoretical point of view here important? So theory of this effect of optical nonclassicality comes to the question about coherent states. Coherent states are eigenstates of the annihilation operators. And these states actually have number distribution, like Poissonian distribution. The number alpha is like a complex amplitude. It's nothing more. Yeah, so this complex number. And here is, you see something like intensity. So this is like a mean value. Intensity is a mean value for this Poissonian distribution. And very well-known results that people understood at the beginning, at the very early times of quantum optics, that any experiment with passive linear optical elements and coherent states can be explained with no need to quantize electromagnetic field. So everything that I have with coherent state can be described by just classical Maxwell equation. I do not need quantum electrodynamics even here. Yeah. The question is where this result is lie on this line, because coherent state is only here, but this is also classical, and this is already non-classical. The question has been done in the papers by Glauber and in the paper by Professor Sudarshan, who presented such a representation for density operators. So quantum state, which is described by density operator rho, can be always expanded in such a way where you have alpha is coherent states, projectors on coherent states, pure coherent states, classical states, and P from alpha is some function. This function can be positive, definite. So this may play a role of probability distribution. Then this is statistical mixture of classical states. And of course, in this case, we do not need quantum electrodynamics. Everything can be described with classical optics. But if this function has negative values or even more serious, it can be highly singular with non-negativity, then we cannot describe this phenomena with classical in terms of classical electrodynamics, and we need to have something that described all this with with quantum electrodynamics or with quantum optics. Here is just some examples of states which both classical and non-classical. Green is classical, for example, coherent states, of course, this classical, and this has such P function, this is like a delta function. Thermal state is just from thermal equilibrium, which we can get, is also classical. It has just a Gaussian, something like a Gaussian function. But when you have, for example, single photon emitted, for example, by an atom, it has already such a strange, this is red column, strange P function, and this is already non-classical. And non-classicality is in principle. So classical states, one more. This is states with positive definite P function. Non-classical states, this is the rest of all. So this is very important in the moment to say that non-classicality now in the modern technology consider it not only like nice theoretical things, but also such as a resource from quantum technology. There is such a branch of research which calls quantum resource theories, and optical non-classicality is an example of a resource which calls optical coherence. So in this case, we say that our resource, so our quantum state, is superposition of coherent states, which are considered as quantum states, and where it can be used. First of all, very nice result that when you want to generate entangled states of photon, entangled state of light, you need, and only you have only passive optical elements. For this purpose, you need to have non-classical states. So entanglement itself is very useful resource in quantum computing and in many branches, quantum communication and so on. In quantum metrology it is used. Very interesting results there exist in quantum metrology. People have shown that also when you have non-classical things, they appears to be useful for quantum metrology. So this is really not a hype in this case. This is really interesting things. And also in non-universal quantum computing. They can be so like a boson sampling. So this is just a resource for all these things. So this phenomena is really interesting. Okay, but how we consider non-classicality in experiment? In experiment, we do not have usually the whole quantum state. In experiment, we consider usually only statistics. For example, photocounting statistics. You have a detector, you have a photocounting statistics, and you have input, which is in quantum states. At the output, you measure a number of photocounts. You have a series, for example, of measurements. After that, you can reconstruct photocounting statistics. But photocounting statistics, this is not the whole information about your quantum states. You should do something like this, tracing with density operator and with these things which calls positive operator value measure, which POVM abbreviation, which describe your measurement device. So when I'm theoretician and, for example, I would like to describe some experiment, it's important not only to calculate quantum states or to solve, for example, Schrödinger equation. It's also important to consider what is my characteristic of my measurement device to find this P of M. This is a separate task, so this is very important because this characterizes everything that I consider. Yeah, but here what I would like to say that we may have, due to this informational incompleteness, very interesting things. For example, rho is non-classical. So this cannot be described by a positive definite P function. Its P function simply has negativities. Yeah. But because there is no informational completeness here, Pm, this probability distribution, can still be reproduced with classical coherent states. Let us consider what this means. Yeah, so this looks like we have lost information. So at the end of my talk, I have shown you our last results that even in this case, we have some surprising things. But first, let's consider this. So my objectives, my goal for this talk is to hold. First, I would like to briefly show you our results about this, how we have constructed this POM, described some realistic photocounting measurements for some widely used experimental techniques. Yeah. And after that, we will talk about identification of quantum resources, in particular optical non-classicality, yeah, with such informationally incomplete and noisy measurements. So either it can be used, so either it's still when you have imperfect experiment with informational incompleteness, with noisy device, can it be still useful? Our answer, yes. Yeah. So even with some insufficient resources, cheap resources, we can get some useful things. Okay. First of all, about this POM. The most ideal detectors that can distinguish you between 1, 2, 3, 4, 5 photons is impossible. Usual detector, very standard detectors in the lab, at least standard, not all of course, but very standard thing in the optical lab. This detector which can only distinguish you between presence and absence of electromagnetic radiation. Yeah, so you cannot say that this is 1 photon, 2 photons, or 3 photons. You can say only either this is vacuum or nothing else. What people do traditionally in this case, one of very interesting way is when you split your beam in a series of some beams, you suppose that here is in each beam something like 1 photon, and after that you detect each beam with one of detectors. You consider how many of these detectors have been clicked, and you think that this is somewhere approximately correspond to the number of photons. This is not true. In this very nice paper by Jan Sperling, Werner Vogel, and Girsh Agarwal, they have shown that the POVM is looking like this. This is not like a pure Sonian distribution, and actually we should take into account. Another well-known technique, so this is so-called superconducting nanowire single photon detectors. This is real nanowire. This is real nanowire, which is operating with near critical temperature in the superconducting regime, near critical temperature. Yeah, so this is a little bit hotter, and this is already in normal phase, and near critical current. Yeah, and when photons comes here, so even single photons with very high probability, this will be absorbed, and you can see something like a voltage pulse in this case. And when you consider it in some time domain, for example, tau m, so you can see 1 pulse, 2nd pulse, you can simply count these pulses, and also the number of these pulses will be approximately correspond to the number of photons. But this is also not true. First of all, why this is not true? Because when you have so ability of this detector to, when photon is registered, the next time ability of detector to register another photon is just very smoothly recovered. First, this is something like dead time, and after that, this recovered. Yeah. So no photon can be detected here, and here this ability just very, very slowly appears. Yeah, in this domain. And this is the problem which tells you what happens inside this domain. But also you should do, in principle, nobody do it, but in principle, in order to get correct result, you should interrupt your process. Because, for example, this pulse can affect you the next pulses. And after that, all calculate. So we have considered this situation. We have considered this situation with some model, with this model for this recovering process. What we have built such a POM. I understand that this is very long theoretical formula. Nevertheless, somebody of you can see that some corresponds to Poissonian formula. And this is our realistic POM. And even more interesting at these results, people in experiment usually never consider this interruption. So this dashed area, yeah? Because usually one do something like this. What happened in this case? In this case, you have a really strange situation when events in one time domain affect you on events in another time, in another time domain. So we have something like memory from previous things. And in this case, very basic, looks like this, very basic quantum rule, Born rule, which should be linear with quantum states. It appears to be nonlinear. So this is not fundamental things. This is just because you have effect, this is not fundamental measurement, yeah? But nevertheless, so Pn probability distribution now non-linearly depends on density operator. And here is something like multi-window POM. I do not want now to discuss, I do not ask you to understand now this equation, just to look at this last equation here, that it has several terms. It says that you have effect from the previous window, from the second but previous, and so on. Usually our calculation has shown that it's enough to use 2 or 3 previous time windows in order to describe photodetection process. Okay, now I move to another purpose of my talk, to another purpose of all these things, and non-classicality of photocounting statistics. Just a moment, okay. Yeah, and let us consider what means this informational incompleteness. Information incompleteness, please, this is not only noise that I told you in detector shortcomings. Information incompleteness even for ideal photocounting detectors will be a subject, yeah? But in this case, informational incompleteness, what means informational incompleteness more formally, from our more formal point of view? Using quantum optical equations, using quantum optics, we can write such an equation for statistics of photocounting, Pn, and it connected with probability, with statistic of photocounting for coherent states, for this classical coherent state. And here we have some averaging. Again, as I told you previously, people who know quantum optics can tell me, okay, this is P function, these 3 things, P function. But let us consider it from a little bit different perspective, because our measurement is not informationally complete. Yeah, this equation, we can consider that P from alpha is some unknown function. So this is something like a set of integral equations, and our task to find all possible solution. One of the solutions is Glauber-Sudarshan P function, but this is not only the solution. When you find this Glauber-Sudarshan P function can be negative, but when you have found another solution for this equation, and this is totally positive, this means that even for the positive definition, for non-classical state, you can reproduce this statistic with classical mixture of coherent state. So it looks like you totally lost information about non-classicality, in this case, about quantum resource. It simply does not exist in your statistics. Your theoretical object, density operator, is classical, is non-classical, but your statistics that you got in experiment is non-classical. Okay, how to check it? So, sorry, again, I have, okay. Here we have, there are a number of things that one can check. We have simply considered it from the point of geometry. Yeah, it's possible. Our student, Vadim Kovtuniuk, has presented some geometrical things. We have before, with our colleague from Mexico, Andrii Klimov, presented another point of view, very similar point of view. But what is a result here? Here we have used geometry, and yeah, this sounds very theoretical, I know, but this is so-called hyperplane supporting theorem. The problem is that all these classical probability distributions in some space of probability distributions form some convex set. And this convex set you can always separate from others. What this means in practice? In practice, this means that if exists such a solution, positive definite, then for any function lambda, such inequalities should be satisfied. In this inequality, left-hand side, this is a mean value in practice of this arbitrary function, yeah, from quantum data. And right-hand side is mean value from classical data that you can now from classical theory of photodetection, or even you can measure it also in experiment. If you found at least one lambda that this inequality is violated, then your photocounting statistic is non-classical. So it cannot be reproduced with classical electromagnetic fields. But this is a very tricky problem to find this lambda. So this is not so easy because this is optimization problem. And here is one of our results, our recent result, that, for example, for some simple cases, for some not only simple experimentally simple, but theoretically this is still a very big deal. Yeah, for some realistic photodetectors, for example, array of detectors that I told you. But for two detectors, you have light beam. Beam is separated by 50-50 beam splitter. Here is detector which can only tell you how many photons only presence of absence photons. So your number n is the number of these clicks. So this can be 0, 1, or 2, nothing more. And we can find in this case optimal parameter lambda. This optimal function lambda. And you can find inequalities, a set of inequalities. That inequalities can be combined in one nonlinear inequalities. This looks like this. And sorry, this is necessary and sufficient condition for this measurement device. Yeah. So if your inequality in this very simple case violated, okay, so your state, but your statistic is non-classical. When it holds true, this is classical. Even in more difficult situation, when you have more than 2 photons, for example, when you have 3 photons, so in this case, you have some geometrical picture, very nice geometrical picture, I will not describe it here, but you also have these 2 inequalities, and this is also necessary and sufficient condition for this experiment. And this can, in principle, be generalized for any number of photons. Yeah, this is a nice and really distinct theory. Yeah, and I just want to show you one example, interesting example as for me when it works very interesting. So there is in quantum optics such interesting states, they called squeezed states. So vacuum. For example, everybody understands that electromagnetic field, this is harmonic oscillators, yeah? And with this one mode of electromagnetic field, this harmonic oscillator. Ground state of harmonic oscillator, it has variance in position and in momentum. The same story exists in quantum optics, but only not position and momentum, but field quadratures, for example, yeah? So this is for field quadratures. And you always have some noise, even for classical state. But what is interesting that it's possible with parametric down-conversion process to make squeezing, so to diminish one noise. So this variance along one quadrature will be less than classical, yeah, than vacuum, yeah. And after that, you can shift it. And if you present, so this is for Wigner function, I don't want now to say that what is Wigner function, some probability distribution in this phase space for real and image part. So for this is so-called phase squeezed coherent state, yeah, for Swiss coherent state. And for this coherent state, photon number is simply looking like distance from origin to here, and you see the dispersion, so sorry, variance is very large, so this larger than vacuum variance, yeah. So nobody expect no classical photocounting statistics here in principle. It does not, it should not exist, and some standard text, something like Mandel parameter and others, they say that this state, so photocounting statistic, photocounting, not state, but photocounting statistic is classical. With our method, we have found that this is not true. With our method, we have found that even in this case, you can observe non-classicality of this photocounting statistic. So this reveal non-classicality in this case. So it's already, and this can be done with really small resources, so with which can be implemented, I believe, in any quantum optics labs, even with 3 photo detectors on off detectors array. So this is not really very serious experimental resources you need for this. Okay, one more example that I want to present you. A very different example. You see this on-off detector. It's impossible to find non-classicality, reveal non-classicality impossible. Statistic of on-off detector, of a single on-off detector, is always classical. It always can be reproduced with classical electromagnetic radiation. But we can a little bit modify this device. How? We can put here some beam splitter with almost transparent, almost transparent beam splitter, and here put so-called local oscillator, laser field with such coherent amplitude gamma I divided by reflection coefficient. This procedure, so this gamma I local oscillator is something like a device setting. So you have not one probability distribution, but a set of probability distribution, conditional probability distribution that is conditioned by this local oscillator. And in this case, you have always almost the same story like in the previous case, but not for probability distributions, all probabilities one probability distribution, but for all probabilities distribution. And only 0 no-click events are important. So this is what you can reconstruct an experiment. And here is very interesting result that you can see that this shaded area, this is actually in this space of probability distributions that you can reconstruct. This is classical area. When you have measured something, when you have measurement results, and this is inside your classical area of this shaded area, so this means that your statistic is classical, so this can be reproduced with coherent states, so with classical radiation. When it's outside, you cannot measure it. Very interesting things that have found Vadim Kovtanyuk in our paper. So this is formalized by these inequalities. Yeah. So this is actually our linear inequalities, but they can be combined just in three non-linear inequalities. So just one of them violated. Okay, this is non-classical. And here is just an example with these green points. Yeah, so for squeezed vacuum states, and we have this displacement, so this is coherent displacement, in the direction of anti-squeezed quadrature. So this again very tricky situation. So so it should be clearly classical statistics. So no classicality should not be detected here. This is different so-called detection efficiency. And you can see that for some, okay, tricky in this case, experimental situation, because efficiency 0.95, this is not really easy to implement experimentally, but nevertheless, even in this case, non-classicality can be revealed. Yeah, so this works. Okay, and in the last part of my talk, I would like to present you another result, which is still under consideration in journal. The question is really intriguing. Okay, I have found that in my measurement statistic, I do not have some signs of non-classicality. I do not have a sign of quantum resources. Can it still be useful? But my state, I know that my state is not classical. Yeah. But here I cannot recognize non-classicality from the measurement data. Can it still be useful? Can I still reveal some non-classicality from here looks like a strange question because, okay, you don't have nothing. You can still simulate, reproduce this result with classical electromagnetic field. Which non-classicality you're saying about? Yeah. Okay, I will show you that what appears is not so easy. And just let us consider such a bit complicated maybe, but I will try to explain you experimental scheme. Very interesting point, how to not only detect quantum state, but how only one can generate coherent state. And there is such interesting scheme which calls conditional preparation. Conditional preparation, this is at least two modes of light are involved. You made measurements on one mode. After you have measurement result, you know it, you have recorded it, yeah? Your wave function is collapsed, and you know that you have on another mode another measurement result, another quantum state. So you make engineering through the measurement on correlated field in one mode in order to show this on another mode. Okay, what is this device? Here we have source. Source of very interesting light. It looks like this. This is so-called phase randomized two mode squeezed vacuum state. Two mode squeezed vacuum state. This state even not entangled. No entanglement in this case. So this is so we can do whatever we want with this. But please look that even no entanglement here. Even more, I can tell, whereas another quantum correlation like quantum discord and so on, it's also without discord. So this is totally uncorrelated state. Yeah. When you consider one mode of the state without considering another mode, this will be just like thermal state, totally classical state. Only correlation can be here considered. So this they have not positive definite P function. Okay, what we do in this case, one mode is sent to one party which we call, Aries, yeah, and another to another guy who is called Bob. Okay, what do Alice? Alice do unbalanced homodyne detection. She can choose setting, local oscillator, usually two possible settings. For example, I don't know, -1 or +1, yeah, in some units. And after that, she can get two results, or click here exist or does not exist. Altogether, Alice have 4 possible quantum states. Yeah, so we can randomly have for Bob here 4 possible quantum states. It's even difficult to call this process like quantum state reduction because state is entangled yet, but nevertheless, the conditional just standard things in probability theory exist. What do Bob? Bob here do this measurement with array of 2 detectors. So again, here is 50-50 beam splitter and just 2 detectors. And each detector can only say you if light exists or does not exist. And NB is the number of detector points. So detector Bob gets these quantum states and he can after that to consider statistics. What situation we consider? We consider the following situation, that the conditional state, so this is, it looks, so theoretically, in some theoretical point of view, from the point of quantum information theory, it can be written like this, so this is 4 possible states. So, conditioned at the Bob side are non-classical, so we understand that they are non-classical. But with this device, Bob cannot understand it. When he simply analyzes it, with our necessary and sufficient condition, Bob totally cannot understand that this state is non-classical. For him, this statistic can ever be simulated classically. Yeah? So he can simply use here classical electromagnetic field, coherent state. Yeah? And after that, just to look, oh, okay, I can do everything with classical field. What quantum is here? No quantumness. Yeah? Very strange question appears. Can one still revolve non-classicality for the teeth with the same data, without some introduction of device modification. And very interesting question, yes, why can? With some restriction, but one can still can. We have present such a concept which calls non-classical steering in this paper. So maybe this is something like a model, yeah? So this is, I still have 15 minutes, yeah? Okay, this is something like a model. Maybe I will explain it in more details. Something like local realistic model in Bell non-localities or model for entanglement they used. So we simply have introduced a little bit different model. What is this model? Let us suppose that quantum state can be it can be described by some probability distribution rho b from alpha. Yeah. After that, source sent. So here is totally asymmetrical situation. Source set on the side of Bob coherent state with this amplitude alpha. And on the side of Alice, he sends just a number. On the side of Alice, things happened like it's in standard Bell inequalities, like in a standard Bell analysis. So Alice says that we have some device setting. After that, she supposes that there is some device response function. This means that this is conditional probability distribution to get value A for some observable A under given this amplitude alpha and setting A, and have some result A. For Bob, situation is restricted. For Bob, we say he has quantum state. This is coherent state, but still it's quantum state. And he has classical probability distribution, and under some settings, he gets result B. After a lot of number of experiments, measurements, we can get such a probability distribution. In principle, this model is written like this. Yeah. Our result, so we called it, it's very easy to another model which calls local hidden states, not classical state, but local hidden states model, where people suppose this is for so-called a phenomena like steering. There is such correlation like steering. When here we have not coherent state, but any state. Yeah. And if we find that this model does not exist, so we have found violation of this model, then this means that there exists non-classicality of at least one of these states of the Bob state, even if they are classical. And actually we have found this. So we have found this, we have used again, we have looked that this model again is a convex set. So one can apply here again this hyperplane supporting theorem. And one can revow non-classicality in this case, even in this case, so even if in this case you have total classicality. So situation totally classical, you can simulate it, but you can still find in your data some, I don't know, signatures of non-classicality. Yeah, I cannot say for which density operator it exists. It's unclear for me. I can only say that at least for one of them there exists quantum resource, non-classicality. We believe that this result could be generalized for more complicated and more interesting quantum resources like entanglement, I don't know, maybe non-locality, maybe quantum coherence and so on. But of course, this is not what we have done now. Now, this is just such a small example, interesting, but okay, this is what we have. Okay, I'm going to summary. What we have in summary in my talk is that photocounting theory with dead time, relaxation time, and after pulses have been introduced. Another our results that tight non-classicality criteria for realistic photo number resolution have been present. And we have demonstrated that we can reveal latent optical non-classicality hidden in this insufficient results via phenomena which we called, okay, we introduced just, not we introduced, and other people introduced, but we have given for this rigorous description, non-classical steering. In the group of Matteo Perez, I should say, this term was introduced from Italy. Here are some our paper about these activities. And at the end, I would like just to thanks to the member of our group. So this work has been done that I was considering here. A lot of things has done Vadim Kovtanyuk, who is our PhD student, Evgen Stolerov, who is here now. Yeah, so and we're discussing with all other students who is here. So I believe that young people do really great work. Thank you very much.
Okay, let's thank our speaker. Now we can ask several questions. We have a time, please. The member of Professor Semenov group.
Actually, I have a question about scenario with two on-off detectors, maybe slide 14, for example. If our probability distributions go out from such a convex set, is it means that correlation will be negative completely?
But we don't consider here for this case. For non-classical set, not necessary. Here is an off detector, it's not necessary. Correlation, you mean between these two detectors, yeah?
Yeah.
Not necessary. It can be, but not necessary.
But
This is more general.
But is negative correlation is
This is on off detectors.
okay? Thank you.
Yes, this is not for the number resolving detectors. This is on-off detectors. This is for on-off detectors. Yeah, but not necessarily correlation is negative here.
Okay,
Can be, yeah, and this will be very good signature of non-classicality, but not necessary. What happens if it's positive, but it's still violated?
But this is not the same thing. This is going out from the convex set and
This is outside, should go outside convex set, yeah. When negative, this means this for sure we know that this is outside of convex set.
Thank you.
Yeah, you're welcome.
Okay, other questions? Please. Professor.
I have one question concerning general foundation of your theory. As I understand, there is a
Sorry.
you use coherent states of Heisenberg-Weil group. Is it vital for your consideration? Can you use another coherent states of another group?
Very good question. Thank you very much. This is why I start this story with some historical things. Yeah, historically it was coherent states, and it has been shown for for Glauber coherent states. Yeah, for states which we call Glauber, but the states comes from Schrödinger times. Yeah, and it was shown that this point that I told that. We can discuss this point. It's differently, so it's discussable. But this point actually comes from very old time and very early in quantum optics, exactly for this coherent state. When you can, with this coherent state, you can always use only Maxwell equation. Stochastic maybe Maxwell equation, but another classification. But if we consider more general context, because today this is a little bit older things, yeah, this is a little bit older and okay, so on. We can consider more general context that non-classicality, optical non-classicality, as a quantum resource, yeah, as a quantum resource. And in this case, exactly this is what you can use another stage, not only coherent stage. People also use Fock stage or another. So this calls phenomena quantum coherence. Yeah. So this is you choose simply some basis, not Glauber coherent state, but another basis, for example. Yeah. And you want to ask question whether your density operator is diagonal in this basis or not. You need some witness for this. And this is in this case, yeah, this is important resource which called quantum coherence, yeah. And this is actually part of the story, yeah.
And a small question, as I am correct, it was slide number 14 or 12.
Just a moment.
You compare classical and quantum case for energy or function E.
Just a moment, I will hear you mean. Or
this one, the second formula, when
this is not energy. This is expectation value.
what is the quantum is understandable expression for E, the last formula on the left. But what is the meaning of parameter alpha in this case? It's
I see. Yeah, I understood you. You see how we can do this experiment? How, in principle, this experiment can be performed? You choose some number. You have first some data from quantum light, from the classical light, which you would like to test. So this is probability distribution Pn. Yeah. After that, you choose some function lambda from n that you supposed will violate this inequality. You calculate this expectation value. This is simply expectation value, nothing more. Yeah. So you can calculate it directly even from your data. This is not a problem. What is here? Here is to hold situation. Yeah. First situation is when you have already theory for your P of M. This is why we calculate this P of M. Yeah. For different detectors. So you simply know this probability distribution Pn from alpha. Pn given alpha. So for classical. So we simply know this. And we can calculate it. But when we look at the physical meaning of this term, we understand that this is for a given coherent state, Glauber coherent state. When you fix some coherent state, this is again the same mean value of alpha lambda. So in another experimental situation, when you do not know this function, it's totally possible because nobody can build theory for every possible detectors. Yeah, and even if we build this theory, we can be wrong. Yeah, what you can do, you can simply do what we call detector tomography. This simply means that you can consider this to build this classical data for different values of classical coherent amplitude, classical light. What is classical light in the lab? This is laser. So you have simply attenuator. With this attenuator has, you can maybe have access to this attenuation parameter here, and you may consider different amplitude. And after that, so this is called detector tomography. And even in the case when we, as a theoreticians, very unlikely to build theory for this detector, in experimental situation, it's still in principle possible to do. Yeah, of course, people from experimental physics now tell me a number of things why they cannot do it. Yeah, of course, but it's our standard discussions. But in many situations after that, this is still possible situation. Yeah. Yeah.
Maybe I ask a stupid question, but it is
no stupid questions. All questions.
But for me, it is interesting. Can be this theory or this consideration be applied to phonon, magnon, exciton?
Yes, it is. I believe. So quasi-particles, yeah, others. Yeah, other quasi-particles. You see, but here is. I cannot say directly that for magnons, for excitons, it's still useful to use coherent states. Yeah, Glauber coherent states. It's a bit difficult, much more difficult sometimes situation. Yeah, and people actually do it.
Boson, but for the,
yeah. But if we consider it in more general context. Not like I was already answering on the question, that not only optical, because this is just very restricted, but optical by bosonic fields, all that I told. Yeah, but if you consider more general context of quantum coherence theory, yes, it is. It's possible to do, and it's possible to for quasi-particles in solids. I don't know how to. I'm not an expert. I don't know how to do it experimentally. You see, but. Theoretically, you can apply it to consider all these things. How to do it experimentally? Good things, because In this case, you need some access to the data. So I'm pretty sure that some experimental techniques exist, very similar to photo detection, command detection, and so on. But I'm simply not an expert at it now. But theoretically, yes, not optics, because optical non-classicality is just a particular example. Yeah, but we use it because it's very easy problem. So we start with easy problem to demonstrate that something interesting here exists. You see, but in principle, yeah, we can.
Okay, thank you very much. Other questions? Yes, Professor Zolotaryuk.
In the case of superconductive detection,
You mean this
superconducting the
nanowire detectors?
yes. You said that the temperature should be somewhere very close to the critical.
Yeah.
Why?
Because this is like the design this detector. You see what we have here in principle. You have here this nanowire, superconducting nanowire, yeah? And in this nanowire, not only temperature close to critical, current is also close to critical.
Wait. Critical, what do you mean critical? Just on critical.
A little bit, Yaroslav, I'm not a solid state physicist, but what I know from this study, that just a little bit more temperature, just, I don't know, some small ratios of kelvins, yeah? And you already destroy a superconducting phase. So this should be, so when one photon, single photon, comes here, and this destroyed one single Cooper pair in this nanowire. Or people discuss if Cooper pair exists there, but okay, for me, I was a student who were listening what Professor Lochlev lectures on superconductivity. So for me, it's easy to think in Cooper pairs, yeah? So in this case, so it destroys Cooper pair. And after that, here, what happens? It appears so-called hot spot. So this means that current already should, so this is a really thin wire, yeah? Really thin wire. Current should already come around this hot spot. But density of current also appears to be larger, yeah? And what happens then? Current is also close to critical, superconducting phase is destroyed, and these hot spots start to growing. This is what you expect. So this is in such voltage this scheme, you see such a pulse. So current simply comes not here, but it comes through the shunt, through the bypass, sorry.
This is like a free electron laser.
No. This is really interesting detectors. This is maybe I was believed when we were writing this paper that this is the most perspective detectors in quantum optics. But after that, people told us that there exist even more nice detectors, transition edge sensors. Yeah. Also superconducting, by the way. Also, they use superconductivity. Evgen Stolarov can talk about this more things. Yeah, but this very big advantage of these detectors is they have a very high detection efficiency and practically no dot counts. So when you say one photons, with very high probability, this photon will be detected. So much better than for other avalanche photodiodes and other things. Yeah, but yeah, this is story I understand a bit expensive, but nevertheless.
So if I understood you correctly, that at those time moments when we see these spikes, the superconductivity is destroyed locally and only locally, but okay, thank you.
Yeah, it's destroyed locally and it grows. Yeah, and after that, this is relaxed to the previous stage, but very smoothly. Yeah, not simultaneously.
Okay.
Yeah, this is very, by the way, so far we have presented theory here more or less phenomenologically because we have just a model for this relaxation. But so far as I understand, there is no still theoretical description on microscopic value for this process, for this relaxation, for a process of this description. There's very interesting physical systems, and there are a huge number of papers on this, but still there is no single point of view how all things happens there macroscopically, from microscopical point of view.
Okay, okay, thank you. Other questions, Professor?
Yeah.
Coherency reminds pure state.
Yeah.
But there are a lot of different type of dissipative processes which destroy coherency. You know nothing about this. Can you say any words about the limitation for coherency?
Yeah, of course, this is actually what we do. Yeah, because environment, this really, when you, coherency, this is pure state, yeah? In standard situation, just a moment, let me look here. So this is why we do not with a vector in Hilbert space, but with density operator. Because in real world situation, we really, you're totally right, we never have pure state. It's simply almost impossible to do, yeah, in optical. Maybe sometimes very, very close to this. But we should consider, theoretically, we should consider dissipative processes and so on. Very close situation to this case, to pure coherent states, is in this experimental scheme that I demonstrated just a moment, for a generation of this state. Yeah, we want to make it pure coherent state, but also, so it can be, so theoretically we can write that this is pure state, not coherent, but pure state. But even in this case, this is not pure. Why? Because you have relaxation properties, first of all, due to photon losses.
But you did not estimate this.
Oh, we know them very well now. Already estimated, it was done not by us and many years ago. Okay. So this is already very good described.
Okay, other questions? Yes, Yuri Mishchenko.
I have a bit technical question to that along definition of a POVM with multiple integrals, exponential. Could you please show that formula, along formula?
Just a moment. Which formula you mean?
Previous.
Yeah.
This one. In the box.
Yeah, okay.
Why are there so many integration and
okay.
How can be understood from basic concepts? Why there is exponential of sigma and what
are these things? Yeah, okay, very good question, but my answer will not be so easy in this case, sorry, yeah. First of all, I would like to tell you that POVM, so this is, you see, to find POVM, this is approximately the same problem as to solve Schrödinger equation, yeah. So this is separate theoretical task. What we have here, I just try to solve. So I don't write here details what this function means, yeah, because it will be very difficult. But in principle, we should consider here something like an effect of this pulse. You see, it happens, this pulse, yeah. After that, your ability to detect the next photon is 0. And after that, it's smoothly recovered. This smoothness we should somehow to describe, somehow to include in consideration. So next pulse happens somewhere here. It depends on the time when happened this time, photon. This is why you have many integrations here, yeah? Because it depends on each time when happened, when this photon, when this process happens. To be honest, such a situation, very similar situation, is shown. There is classical description of Poissonian processes. When you open textbooks on Poissonian processes, or simply on random processes, this is a little bit more complicated than Poissonian processes. Professor will be doing with such things. Yeah, so you can find very similar equations and very similar considerations. Yeah. And this is to explain you details. It's for exactly this detector. Yeah, it will be very. It's really sophisticated consideration. Our theoretical paper on this point contains, I believe, 180 equations or something like this. Sorry. Yeah, this is in figure of A.
Okay.
Yeah.
Okay. Thank you. Other questions? No, yes, there is one question in Zoom. Please, Professor Vakhnenko.
We use some notions such as entangled states, such as density matrix and so on. And the last, your statement was that there is no pure quantum state and we should use the density matrix. How this, your statement, is correlated with the your notion of entangled space states, which supposed to use the particles separated million miles ago. Yeah.
Okay,
It's one question.
Yeah, I got your question. Thank you very much. Look here. First, I will say nothing about entanglement, it seems. Yeah, but okay, it's also quantum entanglement is also resource. You're absolutely right that initially entanglement was formulated for pure state. It's totally correct situation. I'm just, I don't remember which year it was, but 19 or 1990 or something like that. Professor Werner has introduced exactly the same concepts, has generalized this concepts for the mixed state. So in a new formula, in new terminology, in this terminology, it's even called inseparable states. So this is one can many things to say about this, how to say entangled state, but really we should not use in principle in quantum optics we almost never use pure state, yeah, and even mixed states, yeah, even mixed state, which is described by density operator, can be so-called inseparable. So this just additional definition. I can show you after that maybe some textbooks or some references where this discussed, but we consider there are some these correlations, which we called something like okay, generalization of entanglement for the case of a mixed state. But this still exists.
Let us ask you once again. You use the notions that do not strictly defined. You see, for example, collapse of wave function. This only the words. There is no strict theory how to describe this process. You see, so some kind of best-selling story, but not physics. You see.
Sorry, I didn't understand what of wave function.
Collapse of wave function. It's not possible to formalize this process. It's only words. Only words that you speculate from
you mean measuring theory, yeah? You see what we can really say. So let's concentrate. So I don't say now about can I use again? So I don't say about philosophical questions what quantum measurement is. This is really good measurement, good theory. But what is our situation? We have a lab. We have a quantum system, we have a measurement device. What happens during measurement? This is very interesting process, question, but we do not discuss it now. Yeah, I consider only this equation.
It's based on the classic instrument. You see, and there is contradiction between the classic instrument and quantum mechanics. Many people now say that quantum mechanics is incomplete due to this could not describe such notion as collapse of wave function. You see, so most of your talk is pure speculation. I do not see
this is very interesting. Yes, Alexey Alexeyevich.
In pure mathematical terms, it's only words.
Yes, so
Maybe we should not now look. I understand that the role of Professor Einstein, which you take now for you, but I'm for sure don't want to be a bore. You see,
yes.
To have again discussion which was in 1935 maybe, yeah, and after that, so I will be very happy to discuss these philosophical questions, but maybe not in framework of this seminar. So
Yes.
it's really interesting things.
I think we should.
Mathematical calculation.
Yes, Alexey Alexeyevich, we should stop. Unfortunately, we discuss in details this lecture, and
I cannot see anything.
Yes, Alexey Alexeyevich.
General formulas without pure calculation. You see.
Good. Let's thank our lecturer once again.
Thank you very much.
I would like to say that we had brilliant lectures today from our Austrian colleague, Professor Helmut ABELE, and from our institute, Professor Semenov. We had a big discussion, and I suppose we will continue next time. Next year we will have the year of quantum science and quantum technology. So we will have a lot of different events dedicated to these questions, to these problems, and I'm sure that we will have opportunity to discuss all these quantum basics in details. But we should have another one lecture by our PhD student Vadim Kovteniuk, but due to technical reasons he is not here, and we will listen this lecture later. And now we finish our seminar. I would like to thank to all participants that are present here, and all participants which are in Zoom, in Ukraine, in Austria. Let's thank our speakers. And now we closing our seminar and go to coffee break.
Oh, coffee break.
Все, я такий.